morning class and welcome to our lectures on sustainable energy technology. We have been looking at various types of energy storage technologies and their relative importance in the total energy storage capacity that currently is installed in the world today. And we saw, as we are seeing in this figure here, that pumped hydro storage is the largest energy storage technology currently installed by capacity by a large margin. In the other types of storage like thermal storage, electrochemical storage and electromechanical storage have reasonably small footprint, at least till middle of 2017, at which this data is taken from. Of these various technologies, we could see that molten salt thermal storage, lithium-ion battery and flywheels are the most dominant technology in each of their energy storage class apart from pumped hydro storage. So if we look at the growth rates of pumped hydro storage over the years, firstly note that pumped hydro storage is a very old technology. There were pumped hydro storage systems starting from 1909 onwards. Because it's a simple extension of a hydroelectric power plant, clearly pumped hydro storage has had a long and mature history in terms of energy storage applications. However, the true growth of these pumped hydro storage systems started from around 1960 to 1970 decades, after which it grew very fast from very low storage ranges of around say less than 5,000 megawatts, and it grew very fast up to say 1981 when it went up to 80,000 to 90,000 megawatts, and after which it has grown at a reasonably steady pace till 2017 when it is around 160,000 megawatt capacity, which is basically this data here, 160 gigawatt rated power. And you can also see that the growth in the initial phase was primarily driven by Europe and United States, which was followed by Japan from around 1970 onwards, which has grown steadily, and in the more recent decades this has been added up by rest of the world and China, okay, where hydroelectric storage has grown quite fast in the last few decades along with pumped hydro storage. And if you see the current storage capacity growth, okay, which is the global installed energy storage capacity growth over the years, then you see that in terms of gigawatt ranges, this is the growth, not the installed capacity, how much it has grown in a given year. Then you see the storage capacity growth has increased over the last 5-6 years from say around 0.2 to 0.3 gigawatt growth per year in 2013 to around 3 gigawatt growth per year in 2018. And rest of the world is a very important part, but also Korea interestingly has seen a large amount of growth, as well as China, US, Japan and other players. Now this is more of a US centric data here. Here we are looking at the added energy storage and separating it by the sector where that energy storage addition has happened. So for example, so the sectors have been separated into 4 parts. Electric companies, so when they are installing the energy storage in their production systems or associated with grids, then that is one party who is installing these systems. Non-residential users like industries, etc., and then residential users. Okay, and you can see that electric companies are the largest installers of these systems, with non-residential, non-residentials are the next most important, and then you have residential users. And when you look at what type of technology has driven the growth, especially from 2015 onwards, it has been mostly batteries, and this becomes important as we will see that in the last few years battery based, basically lithium ion and sodium sulfur kind of battery based energy storage systems are driving the growth in energy storage capacity throughout the world and in US here, as is shown here. Pumped hydro has installed fitfully, so large growth in pumped hydro in 2013, then a smaller growth in US. This is not true throughout the world. There are places where hydroelectric capacity is being added and associated with it pumped hydro is being added. Okay. But most of the growth in the recent years have been driven by battery based systems. Then smaller amounts of flywheel, thermal, etc. Here is the kind of the growth story of the electrochemical or battery storage. We will also show here that the cumulative battery storage capacity has increased 5-fold over the past 5 years, from 241 megawatts in 2013 to 1274 megawatts in 2018, and this is the important aspect. Thermal storage has also grown, okay, in many places to some extent, okay, so that has also been important. So this is the growth from 1996 to 2016 of the battery storage in terms of rated power, and so it started from around 0 in 1996 and has grown up to 1.6 gigawatts in 2016, and the growth has been an exponentially increasing curve. So battery is increasingly emerging as the fastest growing technology system for energy storage associated with renewable grids. And this is to a large extent because the batteries usage is quite flexible, and many of the intermittency concerns associated with renewable grid are things that batteries can handle reasonably well, okay. But also thermal storage can handle reasonably well. So thermal and battery are the two fastest growing technologies when it comes to integrating renewable grid in terms of improving the grid integration, improving the renewable grid electricity quality, etc. For the next generation of grid systems. So for example, if you look at the applications of pumped hydro storage, most of it is electric energy time shift. So demand supply matching. So when there is low demand, you use pumped hydro storage to store energy and then deliver that extra energy during high demand. This is true for both classical systems and renewables. So the role of pumped hydro is primarily that you cater to the high demand by storing energy during periods of low demand. When you look at the electrochemical, that is the battery group, a large section is frequency regulation, regulating the frequency or the AC frequency of the grid. Okay, so improving the quality of the power. The next most important, this is all the other club together, so this is kind of basic. This is electric supply reserve capacity, so spinning reserves. Okay, if something goes off, this can go up. Okay, electric bill management. So here again, you are basically a type of arbitrage is being looked at during periods of, this is on the user side, during periods of low electricity cost, you are using the energy to store energy and then using that to at least fill part of your demand during periods of high demand when grid electricity cost is higher. Okay. And electric energy time shift, again shifting the demand and supply concepts here. So this is the same as the pumped hydro here. So this is significantly more flexible than the pumped hydro system, which is why battery is being favored in many different applications. Okay. Electromechanical, this is basically compressed air energy storage and flywheel together. Remember, pumped hydro is also electromechanical. We are just separating it out because pumped hydro is such a large fraction of the energy storage space. So here the two most are on-site power. So for example, compressed air energy storage, you are using it as an on-site power generation source. Black start facilities interestingly have a lot of electromechanical groups have a significant part, flywheels and then compressed air systems. Then electric supply capacity and all of the rest. Thermal storage, the largest source is renewables capacity firming. So this is basically the integration of renewables into the grid. You are the technical term here is basically that a renewable firm has said that he will supply this much energy at this minimum rate for a certain period of time. You are guaranteeing the grid supply, the grid who is purchasing your electricity for use. Okay, but obviously wind and solar don't have that kind of a consistent delivery. So you are using the thermal storage system, which can be molten salt, for example CSP systems, to store extra of the solar energy during the day and using it to send that electricity by night. Okay, so that is one example where thermal storage is becoming useful for renewable capacity farming. And renewable energy time shift, this is very common. We are basically using say cold water, as we looked at the airport case, to cool the cold water during periods of low demand late at night, and then using that cold water for building cooling applications during high demand during the day. So it is basically shifting when the demand supply is. Okay. So these are the two major ways in which thermal storage is being used in the modern grid systems. So what we see here then, if you look at the dominant themes, electric energy time shift is the main function of the pumped hydro storage. Frequency regulation is the main function of the battery systems. On-site power generation, on-site power management primarily is the main function of the electromechanical, that is flywheels and as well as black site generation, flywheels and compressed air energy. And renewable capacity farming is the main function of thermal storage. So these kinds of trends, if you look at where what technology is being most used for what reason. So all of this of course depends on the basic characteristics these storage technologies have, and we are just going back to that. This is kind of a nice chart that tells you that it comes from Deloitte, which is a very well known electricity company in energy industry, as well as financials, energy financials. So they kind of published a report on the prospects of the various energy storage technologies, and I am getting this table from them, correct? Okay. So the data is of course 2015 data. There are improvements in all of these ratings because R&D is still going on, but it still gives a reasonably good trend. So for example, if you look at the supercapacitor, its power rating in megawatts is quite low, 0.01 to 1 megawatt. Okay. Storage duration is small, milliseconds to minutes. Cycling is very rapid, 10,000 to 100,000 cycles. Self-discharge percentage, so this is over this storage duration is 20 to 40%. So fast self-discharge times. Okay. Energy density is 10 to 20 watt hour per liter, so it's kind of a volumetric energy density. These data have some non-uniformity. So for example, we will see other data where supercapacitors will have high power rating. So this is being used in a certain way. Anyways, we will discuss those things later. So this is the energy density, watt hour, basically a unit of energy per liter. Per liter is per decimeter cube, so it's per unit volume of the storage material. So energy density is kind of medium. If you look at this chart, power density is very high, so it can generate store a lot of power per unit volume of the system. Okay, watt per liter, 40,000 to 120,000. Efficiency is very high, response time is very fast. So fast response, low duration, high power density systems, supercapacitors. Superconducting magnets, very similar ratings, 0.1 to 1 milliseconds to minute. Kind of self-discharge time somewhat lower, energy density significantly lower, around 6, power density reasonably high, efficiency reasonably high, response times less than 100 milliseconds. So in the same kind of a structure. Okay. Then you have pumped hydro storage. Its power rating is very large. It's one of the largest here, 100 to 1000 megawatts. Okay. Storage duration, it says 4 to 12 hours for diurnal storage, but pumped hydro storage can be done for seasonal storage as well. there is no actual limit of the storage duration in pumped hydro. This is just showing an application where it is being used for demand supply matching, which is usually half a day kind of a system. Cycling time, 30 to 60 years. So it's kind of indefinite in that sense. There is no self-discharge, so it can be stored indefinitely. Energy density is quite low. So you can see the energy density values for pumped hydro are quite low, 0.2 to 2 watt hour per liter. Very low energy density, very low power density, 0.1 to 0.2 watt per liter. So what this means is to deliver the kind of power, it is basically using a large reservoir, right? So it is using a significantly high volume to store that amount of energy. So in terms of energy density and power density, it cannot compete with other storage systems. But why we are using it? It's still quite cheap because you are basically lifting water, and water is one of the most abundant materials. So you can get away with using a large volume of water. So like thousands and thousands of kgs and tons of water are is there in one reservoir. Okay, you won't have that much lithium in the entire world. So if you are having lithium as a battery, you must have much higher power density than when the storage medium is lithium, then storage medium is water. So that consideration comes into play. Efficiency 70 to 85%, response time seconds to minutes. So you can start the flow reasonably quickly to start the power generation by flowing the water down the hill. So response times are reasonable, not in the millisecond range, but still in the second and minute range. Compressed air energy storage, very similar to pumped hydro in terms of power ratings, storage duration, cycling times, self-discharge times, none of them. Energy density is somewhat higher, power density also somewhat higher. Efficiencies are lower because of the pumping cost associated, response time is similar. So these two are again same to same almost, right? They are basically can be used interchangeably. Of course, compressed air requires natural caverns, that minimizes its applications. Flywheels, power rating is again quite small, 0.001 to 1. Storage duration is second to hours. So this can, unlike supercapacitors and superconducting magnets, it can store around for an hour at least the amount. Cycling times are again large, 20,000 to 100,000, just like supercapacitors. Self-discharge 1.3 to 100%. So by an hour or something, it will lose its entire energy. So basically that's the kind of the upper limit in this context. Energy density is significantly higher than everything else we have discussed so far in terms of watt hour per liter, and power density is lower than similar to superconducting magnets but much lower than supercapacitors. Okay, so if you want very high power transmission rates, you are going for supercapacitors. Then if you have medium power transmission rates you need, then you can look at flywheels or superconducting magnets. Efficiencies are somewhat lower, 70 to 95% because of the frictional losses. Response time 10 to 20 milliseconds, again the same as supercapacitors. So again flywheels are within what you would, so flywheels, supercapacitors and superconducting magnets can be used interchangeably. Only difference here would be flywheels can store power to a somewhat larger time usually, and they have somewhat lower energy density, somewhat lower power density and somewhat higher energy density compared to these two. Okay. Then you have the battery system. So traditional lead acid battery power rating can be very low, very small batteries to very large. Storage duration 1 minute to 8 hours. This is typical usage that we are talking about. Again, the self-discharge time within this period is 0.1 to 0.3%. So you can use a lead acid battery for and store that energy for several weeks, certainly several weeks or a month also. Cycling 6 to 40 years. So 6 to 40 years. So it's a long time systems. Good energy densities, lower power densities. So again, from flywheels, capacitors, if you go to batteries, power density is going to decrease. efficiency 80 to 90%, response time within a second. Okay. Sodium sulfur battery, reasonably similar. It can have a higher power rating. You can start with a higher power rating because it's a stationary battery system. It's a molten battery, as we discussed. So you need a reasonably big system to make it work. So the lower power rating is 10. So it's not a stationary battery, as I would say. Cycling, 2500 to 4400 cycles can happen. Self-discharge, this is because it's a hot system, so there are significant corrosion losses, heat related thermal degradation losses, etc. So its cycle life is lower than lead acid batteries. Self-discharge time between in around 8 hours is around 20%, so it can go around 3 or 4 days maximum, at maximum. It has better energy density than sodium sulfur batteries, but than lead acid batteries, but lower power densities. So if you want to store more energy per unit volume, go for sodium sulfur batteries, but if you want higher power, go for lead acid batteries. Okay. Efficiency same range. Response times are quite fast, 10 to 20 milliseconds, because it's a flow system, molten system, so it can respond quickly to fluctuations. Lithium ion batteries, again you can go from ultra portable systems to large installations, so 0.1 to 100. Again the storage duration is the same, self-discharge times are same as lead acid batteries. Cycling, it can cycle 1000 to 10,000 cycles, so somewhat lower than a lead acid battery. Lithium ion batteries have a somewhat lower duration. Energy density is highest till now among the battery systems at least, and overall here the energy density you are seeing, you are getting the highest so far. Okay. So in terms of volumetric energy density, lithium ion batteries are very good as energy storage mediums. It also has very good power densities. Okay, 1300 to 10,000. So we are kind of approaching flywheels and even the lower end of supercapacitors in that context, and much 10 times higher energy densities. So clearly this is why lithium ion batteries is a very good choice for many energy storage applications, and it has very good efficiency, 85 to 98%, and response times are 10 to 20 minutes. So fast response systems, high energy density systems, good power density systems. Concerns are it will take around so self-discharge time is 0.3, so you can store energy for a month or something, right? So that's the kind of the system you are looking at, and it has very large scale range, 0.1 megawatt to 100 megawatts. So that gives it a very good flexibility, which is why it is used in many places. Flow batteries, the vanadium redox flow batteries, that kind we discussed a little bit here. Again, the power range is similar, but it's a stationary battery system, so you are going from 1 to 100. Again, the storage duration is similar, the cycle times are similar. It has good cycle times in that context actually than lithium ion batteries. It's one of the advantages, 12,000 to 14,000 cycle times. It has the highest number of cycle times in all batteries, so that makes flow batteries useful and durable. Okay. But it has lower energy densities and lower power densities, so you are getting longer cycles and longer life, but at the cost of lower energy and power densities and lower efficiencies. Okay, so those things have to be taken into consideration. Then you are making hydrogen based storage systems, which we will discuss in detail very soon. Power ratings very diverse, 0.01 to 1000. You can have small hydrogen based fuel cells, for example, to very large fuel cells or even combustion systems. Large gas turbines can be run on hydrogen only. So you can have power ratings from 0.01 megawatts to 1000 megawatts. Storage duration also highly flexible, minutes to weeks. It can go for a year also if needed. Okay, because hydrogen is stable. If it's compressed and stored, it can stay indefinitely without breaking. So cycling 5 to 30 years. So again we are looking at how pumped hydro storage is looking, how CAE is looking. So you have very large cycles, so you can extreme durability of the storage media in that context. Okay. Self-discharge, 0 to 4% within that time. Whatever leakage is happening, that's what we are discussing here. Good energy densities, actually the highest so far, 600 watt-hour per liter. This is compressed hydrogen, one of the best energy densities, nothing else can compare, even for lithium-ion batteries, etc. Okay, so you can get very good energy densities. I am not entirely sure whether this data, so hydrogen can be stored multiple ways. I will have to check whether this is liquid hydrogen or compressed hydrogen. We will look into detail what the storage values are in that context, but you can have hydrogen storage at very high energy densities as well. Reasonably good power densities, but lower power densities than many of the battery systems. So clearly this is not for a high power application. Okay, you can have 0.2 to 20, so this is kind of a fuel cell we are looking at. I would expect. So you have reasonably low power densities but high energy densities. Another disadvantage is the efficiency, 25% to 45%, the lowest efficiencies so far. Okay, and this has to do with the losses associated with creating hydrogen, compressing and storing hydrogen, and utilizing this hydrogen. This entire process creates a lot of losses. So you have the lowest efficiency among the systems. A lot of R&D's work going on to improve that efficiency, because if that efficiency is improved, hydrogen will have some, at least in some respects, the most superior kind of energy storage medium. Okay. Response times are good, seconds to minutes. Synthetic natural gas, very similar kind of a structure as hydrogen, again a chemical storage system, and you will see very high energy densities. Okay, but of course it's natural gas, so it has carbon. The carbon has to be sourced from somewhere. Okay, so that is one concern in terms of sustainability applications. Everything else will be similar. Then finally, closing this section is molten salt. Reasonably good power rating, 1 to 150 megawatts. So large installations are there for molten salt, especially associated with CSP systems. Storage duration in the period of hours, you are storing thermal energy, so you do not expect a lot of storage duration. Cycling time, basically the lifetime of the system is 30 years or more, so obviously molten salt is very stable, so it doesn't degrade. There is no self-discharge time. This is not true. I am not sure why they are saying it, because obviously you are storing heat. So you have a significant self-discharge time. So there is a mistake from their end on this part. Good energy densities. Of course, this is the only thermal storage system that has been discussed here. So this is thermal energy per liter. So it doesn't actually compare with anything here. All right. Power density does not apply because you are using thermal. Efficiency is 80 to 90% again within this period of few hours, and response time is in minutes. Okay. So this kind of gives us a very good overview and comparison of what are the weak points and strong points of the various energy storage technologies. I would ask you to look in details. Some of the figures may be different if you read further, as I already pointed out here, but they give us a good significant snapshot in this context. So I will stop here. It is continuing here on how it matches in energy density and a power density curve, but we will discuss this in the next class as we are out of time. So thank you for listening, and hopefully this was enlightening, and we will come again in the next class with further details on energy storage technology. Thank you.